outflowing velocity, you'll get an outflow generated. This is basically what Wingley did. Dan Welling has a nice paper kind of exploring that in more detail. And the plus side of this is it's really the easiest thing you can do. The downside is that inner boundary density isn't responding to any causal input. So has pluses and minuses. Another approach people are using is an empirical specification of the outflow. So in this case, what they do is they look at empirical studies. So this is an example from Bob Strangeway. There's also a similar thing from Yuhua Zheng. And here, what Bob did is he looked at fast data, looked at the pointing flux and the soft electron precipitation, and found the correlation with the ion flux observed at fast altitudes. And so from this, you can basically set up a black box approach that the models can calculate these two quantities, and then those can be inputs to this empirical relationship, so you can get the ion flux. And then you make some assumption about how it's partitioned between H plus and O plus, and how you partition that flux between density and velocity. And you can get basically a pretty reasonable specification of the outflow source. And this is really, great if you want to understand the causes of, or if you want to understand the consequences of outflow, and you want to get an outflow source that varies realistically with incoming drivers. The only drawback to this approach is that there's, no physics in it. It's, really a black box. So it's not good if you want to get into the underlying mechanisms of the outflow. So for that, you go to the third approach. So that's first principles modeling of the outflow, and that's great if you want to, do studies that are trying to get at what are the physics of the outflow. The downside is that they're computationally expensive, and your model's only going to be as good as the physics that you included. If you're missing physics, it'll limit your conclusions. So again, you choose the type of specification that represents the study that you're trying to do. So I showed reference to my papers for including first principles as an outflow specification. There's actually some new results from the GEM focus group looking at ionospheric outflow. So this is coupling the Utah State general polar wind model, which I'll talk a little bit more about later. And this is right now one-way coupling. This slide came from Dan Welling. And even though it's one-way coupling, there's no feedback, so they're just taking the outflow specification and setting the inner boundary and then seeing what happens. If you look at the comparison with data, it's actually pretty nice. So I encourage everyone who's interested in this topic to go to the outflow session and see what's going on. So I want to take a step back now and talk about the pathways of ionospheric outflow. So we've talked about how do you track it, we talked about how do you specify it. So now, what's actually driving the outflow? Well, this is a nice summary from Shunk and Soika, 1997, showing all the different things involved in modeling outflow. So the first thing on the list here is the superthermal electrons. So these are the soft electron precipitation in the cusp, the photoelectrons, the polar rain, and auroral electrons. And these work by effectively reducing the potential barrier and providing heating for the thermal electron population. There's centrifugal forces due to field line convection and curvature change. This is more important at high altitudes, and I think there's some studies showing that it's like a 10 or 20% effect. Transverse heating of ions as a result of wave-particle interactions. So this is a very important process for generating conics. So if you have, a broadband wave turbulence, you can get this heating perpendicular to the field line, and that will generate a mirror force that will accelerate the ions parallel to the field. There's non-resonant interactions with waves, so conjugative forces about phase waves. So this, you can see lots of papers about this from George Kazanov and others. It's pretty effective, at generating outflow as well. There's also less discussed mechanisms, including field line currents and frictional heating driving upwelling. I'm just gonna, since I have limited time, I'm just gonna move on. There's So for the effect of superthermal electrons on outflow, this is a figure from one of my papers, but it's actually comparing several different studies. So this on the left is an altitude profile of the log of the electron density, and the dashed lines are cases with no superthermal or very low superthermal electron densities, and these are studies with high superthermal electron densities. And what you find is when you have a lot of those superthermals, you'll get larger densities at low and at high altitude. You also get a larger fraction of O+ at high altitude if you include significant superthermals. There's a nice paper from George Kazanov in 1997, looking at this altitude profile, and here is the percentage of the photoelectrons at the base of the field line. And really, you don't need very high percentages to get a lot of O+. The color bar is the O+ ratio. You don't need a lot of these superthermals to get a lot of O+ at high altitude. I'm not going to belabor this point anymore, but the secondary electrons, are also very effective at generating outflow. This is also from George Kazanov. And if you're interested in this topic, I'll have a poster on Thursday talking a little bit more about this issue. So for wave-particle interactions, those are also included in some models of ionospheric outflow. So on the left, this is the GPW model from Utah State. So in this model, they're tracking the solution along multiple flux tubes that are moving around the polar region. And this is kind of a Lagrangian approach. By following all these flux tubes, they're able to reconstruct the 3D solution. And this is a hybrid type model. So along each of those field lines, they're solving a hybrid solution with macroscopic PIC ions. But the wave heating terms are empirical based on DE observations. There's a description of archive chunk about this. But you don't have to do a hybrid approach or a Lagrangian approach. So there's a new model now, the IPWM, Ionosphere Polar Ring Model from Roger Varney, which was published this year. And this is a very nice approach using 8-moment fluid solution for the outflow on an Eulerian grid, and with a separate fluid to track the heated population. And, but in both of these models, one of the issues is that the heating terms are really empirical. They're drawn from DE data, which is fine, but we don't have actually many good sources to represent how that heating should look like. So I think we really need, from the data community and maybe for future missions to get better wave specifications. And since this is, all about system modeling, I want to talk about what I feel is a shortcoming in terms of representing the wave-particle interactions in the current coupled models. And so if you look at Barkat and Chunk's paper, you see they're tracking this field line that's moving around the polar cap and through the cusp region, through the polar cap, through the aurora. And they look at the effect of the altitude distribution of the perpendicular temperature with wave-particle, or without wave-particle interactions and with wave-particle interactions. And you see that you get, of course, a lot of perpendicular heating when you include the wave-particle interactions. Now, if you look at the altitude range, the inner boundary of most magnetosphere models is around 2.5 RE or 1.5 RE altitude. That's this red line here. So you see actually a lot of the wave heating is happening at pretty high altitudes. So if you're going to regulate, the inclusion of the wave-particle interactions only to the outflow model and just take the fluxes at the inner boundary, you're going to miss all this additional heating and potential acceleration from the mirror force. So this is one of those cases where probably extending, MHD is required. We extended MHD to go to multi-fluid to track the outflow. Now to include the waves, you have to at least include some pitch angle and isotropies. So probably the minimum extension you can go to is the anisotropic MHD equations. These are from Xing Men. And the advantage of this is now you can have separate parallel and perpendicular pressure. You also get a term in the momentum equation that looks like a mirror force. It converts random perpendicular motion into organized parallel motion. And you can add, a heating term, to the perpendicular pressure equation. You can even use exactly the same heating terms that are used in the outflow models. So I just implemented that as a proof of concept So this is, the magnetosphere with anisotropic MHD and no wave heating term. And here I impose a wave heating term over the polar regions. And you see that when you do that, you'll get, of course, larger field line velocities coming away. So with that, I want to leave the topic of ionospheric outflow for the time being, and I want to go to the intermagnetosphere. And I want to talk. There's a lot you can talk about in the intermagnetosphere, but I'm going to focus on the ring current, mostly because limited time. So the global MHD models don't include the drift physics that's required to really capture the ring current accurately. There are extensions of MHD that do include this drift physics, but as far as I'm aware, there's none of the global models are making use of those equation sets. But we do have a lot of bounce average kinetic ring current models and other ring current models that do include the drift physics. And so if you put those two approaches together, through model coupling, you can get a lot of advantages. For the global MHD model, you can get an improved representation of the intermagnetosphere pressure, you get better region 2 currents, and a more accurate representation of the magnetic field. From the ring currents perspective, most of them are being solved inside of an externally specified fields. So here you can now get more accurate representation of the fields, and you can also get dynamic and MLT dependent boundaries. So as far as I'm aware, the first attempt to do this was in Darren Dazou's paper, 2004, where they took the RCMs, these are RCM equations here, and put this into BATS-RS using the space weather modeling framework. And the basic idea is that the global magnetosphere is interacting with the ionosphere through a Poisson equation. So field line currents go in, get combined with the conductance model, and that gives you the polar cap potential. That potential is then used to drive the drift in the intermagnetosphere. Field lines are traced, to give you the fields to solve the intermagnetosphere in, and also the boundary condition for density and pressure are passed. Then the intermagnetosphere, the RCM model, is solved and then passes back the pressure, which pushes the pressure in the BATS-RS equations. So in this first coupling, what they showed is that you get larger pressure in the intermagnetosphere when you have the ring current. You also get clear region 2 currents forming. Now this isn't unique to BATS-RS or SWMF. This has been done with LFM and OpenGGCM as well now. This is an example from LFM coupling, so this is from Asher Pembroke's paper. And as you can tell, when we're doing model coupling, we tend to love these wire diagrams. But I'm not going to go through all the details. I'll just say that while there are some subtle differences, the general concept is the same. The MHD code is passing fields and potentials, and the intermagnetosphere model is solving for the pressure inside and passing it back. So again, you can see that when you have no coupling, you get a lower ring current compared to when you have coupling. You can also see an effect on the fields. This is showing the delta VZ, the equatorial plane, and you see when it's uncoupled versus when it's coupled, you see a significant effect on the field. So those were examples with RCM. There's other ring current models that are different from RCM, and the main difference is that they account for the pitch angle anisotropy. So I'm thinking of CRCM or CINI now at Goddard, or Heidi at Michigan, or the RAM code at Atlanta. And I'm not going through all the details of the wire diagram, but the main change now is that the boundary condition, instead of just passing scalar pressure, passes parallel and perpendicular pressure. And then the model calculates parallel and perpendicular pressure everywhere in the intermagnetosphere domain to pass that back. And this is a case where you have to use anisotropic MHD in order to be consistent. So you saw there was effect on the pressure before. If you were to look at the potential in the intermagnetosphere, so this is the equatorial plane, and these are potential contours. So this is when you include the ring current coupling, and this is where you don't. And you see, the potential is very different. You get this characteristic skewing when you include the ring current, whereas you have this straight, convection pattern when you don't. If you look at the last closed field line, so these ISO surfaces are showing the last closed field line when you're coupling the ring current model and when you're not. So coupling is green and no coupling is purple, and they're translucent, so you can see them on top of each other. And you see the magnetosphere becomes blunter, the standoff distance increases, and so you have a number of effects so far. You include the ring current model, you get a change in the pressure, you get a change in the electric field, you get a change in the magnetic field. And what I'll show you is you actually get changes outside of the inner magnetosphere. This is from Dan Welling's recent paper coupling the RAM SCB model into SWMF. And they were looking at the effect on the ionospheric outflow. And when they had one-way coupling with the ring current, no feedback, they got one solution for the outflow, and they got more outflow when they included the ring current feedback. In fact, they also got more O plus into the ring current, carrying the energy density when they include the feedback. So ultimately, this is really a coupled system. You change one piece, and another piece that you think probably isn't related will also change. So, there's a lot of reasons to go to this coupled approach. So I'm going to move on to the inner magnetosphere now, and for the remainder of the talk, I want to focus on reconnection in global magnetosphere models. So this is the last part. Now, when I think about reconnection in global magnetosphere models, I typically start thinking about the generalized Ohm's law. So if you remember, E equals minus U cross B is the ideal MHD Ohm's law. And so this is a statement of the frozen in flux condition. So if you have two parcels of plasma at one time connected by a field, at some later time they will remain connected. If you add another term in the Ohm's law, you can go to resistive MHD. And so here you start having some loss of ideal behavior. So field lines that two parcels of plasma that were initially connected will now no longer be connected, if they pass through this diffusion region. And actually, resistive MHD is what represents most of the modeling that we're doing for the global magnetosphere, where the resistivity model comes from either physical resistivity model or it comes from numerical resistivity. Now I showed the Hall term as well, so if you go to the next term in the generalized Ohm's law, you'll start getting Hall physics. And so here, inside of the ion inertial length, the ions will decouple from the field while the electrons will remain frozen in. You'll get this, characteristic quadrupole signature. And from the gem reconnection challenge, we know that this is kind of the minimum extension you need to get fast reconnection. And I mentioned this because I'm actually going to talk about it a little bit later. We're starting to see more and more extensions to Hall MHD. So the next issue is, how do you define reconnection in the magnetosphere? There's actually a lot of competing definitions of reconnection in 3D. I'm not going to go through them all. I think you could give an entire talk on just that topic alone. But I'm going to focus on something called separator reconnection. So the idea here is, if you look at this picture from Dungy, everyone knows and loves, and you were to color code all of the different regions by the magnetic topology, you'll find these regions where the four topology types intersect. So these are your X lines. But you can actually extend that concept into 3D, and in 3D you would then trace out a whole line that encompasses the set of these points. So this is an example from OpenGGCM where this yellow line is the separator. It's for northward IMF. The nice thing about separators is you can find them for any IMF orientation pretty much. But why would you want to look for them? What's the point? So here's a case. This is for southward IMF. We're looking down on the equatorial plane. And these points are separator points that I've traced out. And then these are the nulls. You see the separators connecting the magnetic nulls. And by definition, this line has to enclose all of the closed flux in the system. If you're to do a path integral of the electric field of the E parallel around that path, by Faraday's law, that would have to give you the rate of change of the magnetic flux. Since the open flux and the closed flux have to match, this is telling you the rate of change of open flux or open flux reduction. So that's one definition of reconnection in 3D. So, of course, I didn't invent this. There's several papers. I think the best overview comes from Lau and Finn in 1990, but there's many others you can look at. It turns out that tracking separators is really hard to do, but Colin Komar, who was at West Virginia with Paul Kasich, and now at NASA Goddard with us, developed a method as part of his PhD thesis. And I'm not going to go through the details, although I encourage you to read Colin's paper, but it's very effective at tracing the separators for arbitrary magnetic field orientation. And so this is just an example looking straight on. So he ran a bunch of resistive MHD simulations through the CCMC and was able to track how the separator is changing with different magnetic field orientation. You can actually, though, even apply this for very complex cases, not high resistivity, but low resistivity. You know, cases where lots of stuff is going on. So this is a case where, sorry, it's hard to see on the monitor, but there's an FTE forming at the subsolar point in this simulation. And the separator is actually splitting into three branches. So you think about, you know, a separator in 2D, you look at the FTE and you'd say, okay, there's two X points and this O point in the middle. If you look in 3D, what you have are these three topological separators. Interestingly, the E parallel in the vicinity of the FTE actually drops, indicating that, you know, the presence of the FTE here is actually reducing the local contribution to the open flux production. There's another complex case you could consider. KH instabilities are seen, you know, fairly often on the flanks. So here you can see the, you know, equatorial plane. You see the vortices. You can trace the separator right through those vortices, and you can see, if you look at the parallel, how the reconnection rate is being modulated by the presence of these vortices. So so what I've talked about so far has to do with, you know, the first two terms in the Ohm's law. So the ideal, you know, up to resistive MHD. But I want to switch gears now and talk about, you know, the extension to Hall MHD. But it turns out that Hall MHD is really difficult to do for the Earth's magnetopause. And the reason for this is that if you want to resolve the ion scale effects in Hall MHD, you have to really separate the ion scale from the diffusive scale. And so if you want to rely on numerical resistivity to do that, you really need 5 to 10 points for ion inertial length. So if you want to uniformly resolve the magnetopause at this level, you can do a simple calculation. It would require billions of computational cells, which is a lot. So, but it's not hopeless. So you can actually, you know, look at comparative magnetospheres. And so these are, you know, different magnetized bodies in the solar system. And if you were to calculate the ratio of the ion inertial length over the characteristic length of the system, in this case we chose the distance to the magnetopause, to the subsolar magnetopause. You see for Earth that ratio is 0.005. It gets better as you go to Mercury, 0.001, but it's really great when you get to Ganymede. You know, the ion inertial length is really huge compared to the characteristic size of the system. So in this case, you can actually model that magnetosphere with adequate resolution for DI with tens of millions of computational cells, which is much more reasonable. So, you know, now we did this simulation. So this is a paper by John Dorelli. I was involved in this work as well as our friends at Michigan. This is using BATS RS. So this is with resistive MHD. Ganymede simulation, and this is the Hall MHD Ganymede simulation on the right. And you see a lot of differences. You see you have symmetric Kelvin-Helmholtz instability in one case and asymmetric KH in the other. If you were to look at the flow arrows, you would see that the drift is very different in the Hall MHD case versus the MHD case. If you look at the field line currents that are mapping down, you'll see they're, again, very different in the Hall case versus the MHD case. And this solution isn't unique to BATS RS, even though we use BATS RS for that. This is an example from OpenGGCM. So this is recently OpenGGCM added the Hall terms. This is from Liang Wang, and they're doing comparisons with the BATS RS results. And overall, the comparisons are pretty close. There are some differences we're still trying to sort out, but I think the general picture is similar. The problem with going to Hall MHD is that you don't include any finite Larmor radius effects. So you can ask, well, how much do the finite Larmor radius effects end up canceling? And so there's a really nice development from the Michigan group embedding an implicit pick code into the SWMF. So basically in their BATS-RS grid, they can define a region that would be solved by pick, and then the rest of the region would be solved by all MHD, and they would have some overlap region where the models are exchanging information. And there's a nice numerical test I'm not going to go into demonstrating that the code actually works. But in the case of Ganymede, it turns out the magnetosphere is so small you can really cover all of the interesting regions with pick regions. So this is from Gabor Toff at Michigan. He gave this presentation at GEM showing these pick results, and I think has a recent paper submitted. And you can directly compare, so he gave me this movie, you can directly compare the Hall MHD on the left and the embedded pick solution on the right. And there you go. And, you know, to my eye, it's actually, there are definitely differences you can pick out, but it's actually largely similar. Both models will give you this asymmetry in the cage vortices. Both of them will give you this very, you know, similar convection pattern. And while there are differences, I think the two pictures are pretty similar overall. So you can make an analogy, I think, if you put all these things together, you can look at the resistive MHD, the Hall MHD, and the embedded pick. I apologize, the formatting is not the same. This was a separate visualization. But if you remember the GEM reconnection challenge, there were several reconnection simulations done with the same boundary conditions, the same initial conditions, but they're run with hybrid, with pick, with with Hall MHD, with resistive MHD, and it was the models that included the Hall physics that gave you fast reconnection. And so I think there's an analogy you can draw here, where again the models that, but this is for a real magnetosphere now with actual data available from the Galileo spacecraft, that when you include the Hall physics, you actually get a different picture than if you don't include it, and the overall picture is seems to be captured by including the Hall term. As my 4-year-old daughter would, she watches Sesame Street, she would look at this picture and start singing how one of these things is not like the other one. So finally, the last thing I want to show is that you don't just have to stick with the generalized Ohm's law approach. You can go to a multi-fluid, multi-moment approach, where instead of multiple ion fluids, you now have ion and electron fluids separately. So this is work being done by the OpenGGCM group in collaboration with the group at the Princeton Plasma Physics Lab. So this is a test case, Orszag-Tang test. And in this case, what they're trying to do is they're taking the multi-moment, multi-fluid code and embedding it into OpenGGCM as an alternative to the generalized Ohm's law approach. And this is just a simple Orszag-Tang test. That's a standard test for MHD plasma codes. And you see in the MHD solution, you get one thing, and if you do Hall MHD or if you do multi-fluid solution, you'll get the same solution in these two cases because they're both including this Hall physics, but not in the MHD case. So this was courtesy of Meng Wang at UNH. So that's it. I think I'm pretty much out of time. So, I don't really have any fantastic conclusions except to say that there's really a wide variety of modeling going on to study every aspect of the space environment, and more and more of these models are working together, and we're extending the models to try and capture all the multitude of scales and processes that are required. So, thank you.
Thanks, Alex. We have time for some questions, so please go ahead and select the questions that you'd like.
Wow.
Okay, that's fair.
Bill, go ahead.
So the impression I have about the reconnection rate is that invariably it's Petrek, right? And it scales like a so there are clearly differences in using Hall MHD in a global simulation. We showed, at least in the regime where the inertial length is large, on the scale size of the system, that we get significant asymmetries. In an Earth environment, I wonder how that plays out, given what we know about the reconnection rate.
Well, that's a very good question. Ganymede is a very small magnetosphere, and how this scales up to an Earth-sized magnetosphere is an open question. It may not scale. I have no idea. Veslav?
To comment more on the question, you and I talked about this particular issue, so I thought I'd mention it. I think this is about coupling the global mosquitoes and the real-estate codes. I think we all have a very significant challenge that the real-estate codes are very good at doing victories, but they're not good for tracking high-speed flow. On the other hand, global mosquitoes now show high-speed flow in the plasma sheet, but they're not good at doing victories. There is a transition region between the hemisphere, slow flow region, and the plasma sheet is dominated by fast flow. There is a transition region where both effects are important. And I don't think any of the coupled codes actually do this transition region well. So
Yeah,
I think that's an important issue for all.
I agree with that statement. I think that the MHD is giving you the fast flow and region pretty well, but it's not giving you the drift physics. The intermagnetosphere codes give you the drift physics. You do have a matching issue on the boundary, and how you deal with that, I think, is still not well resolved. So yeah, it's a good point. Any other questions or? Okay, thank you.
Go, wait.
Okay, sorry. I was wondering if you could talk about data model comparison, and the intro said you never look at data, but I did want to say that we looked at data together and compared it with our paper on the open-closed boundary, which is about to come out, and then Alan Probes. But I was wondering if you could speak more generally to that challenge with respect to modeling and new measurements and all that.
Well, yeah, so modeling, I think, can be a good driver of the measurements. You can come up with predictions of things to look for. You can also try and explain the measurements that you have with the way I looked at it in your paper, how close you are to the open-closed boundary and whether that can be causing dropouts and then Allen probe observations. In general, you have to be very careful that the model that you're doing, the modeling that you're doing is appropriate to the data you're trying to look at. So I think the short answer is it's very useful, but you have to be careful.
So what you're saying is you should look at data.
Not if you're a supermodeler, you don't have to look at it.
All right.
Okay, so that brings to close the tutorials for this morning. I just wanted to summarize the sessions that will be going on after the break at 10:30. We will have the tail, environment, and dynamics at lunar distances. That will be in Salon 2. I'm not sure which of these becomes Salon 2, but I'm sure the number's out there on the door. In Salon 3 and 4 will be ionospheric source of magnetosphere plasma, measuring, modeling, and merging into the GDCM. And then in Salon 1 will be testing the proposed links between mesoscale, auroral, and polar cap dynamics and substorms. I did check during the break. The link on the website now has the updated schedule with the actual rooms in it, so if you want to go download that, you can. Are there any other housekeeping announcements, or anything like that? Okay, break. I believe it's out there, and the view is that way. Thank you. Toshi, come on up and grab your dongles.